Next is Daniele MORO. Daniele MORO is a software engineer at Google, researching the quantization of deep neural networks for constrained application-specific edge inference. As a Boise State Top 10 scholar, Kleiner Perkins Engineering Fellow, Carnegie Mellon Robotics Institute Summer Scholar, and Barry Goldwater Scholar, Daniele graduated from Boise State University with a degree in computer science and a minor in applied mathematics. Through his work on the QKeras quantization framework, Daniele is ardent in his goal of bringing efficient machine learning inference to everyone. Welcome, Daniele.
Thank you. Great. Sounds like you guys can hear me. So yeah, thank you all. Thank you for being here. So in this presentation, I'm going to go into some more technical details. So we'll try to get energized here. So what I'm going to be talking about is about two tools that are open source that we've developed in Google that you can use right now. And these tools are to help you optimize your models. We've integrated a lot of the state-of-the-art research techniques that you've heard about the past 2 days into these tools. So I hope that you'll consider using them and contributing to them as well. And before I start, I'll say that this is not just my work. There's many teams at Google working on this, and specifically the application-specific machine learning team and the Vizier team. OK, so I think we're all here. We know that quantization is great to make models tiny. If we look at this from an energy perspective, maybe a more theoretical perspective, we see a 16x reduction in energy going from float 32 to int 8, and a 1024x reduction going from float 32 to binary. Okay, and you're going to see similar kind of order of magnitude savings when you look at, say, latency, memory, et cetera. You've heard about this stuff in the past few days here, right? So we definitely want to quantize. But how can we do that? Well, first you have to start with some framework where you've built your ML model. And one of the most popular ones and easy to use is Keras. Right? Keras makes it really easy to build models layer by layer using TensorFlow. So what we decided to do is create a quantization extension to Keras. We're calling it QKeras, right? We love the letter Q. You can just add it to anything and it becomes quantized. So with QKeras, this is a drop-in replacement for quantizing Keras layers. So what does QKeras have, right? Like you've probably heard of these quantization frameworks before. Now, this is definitely not comprehensive, so take this with a grain of salt. Also, things change all the time. But I've tried to highlight some of the key features here. So obviously, QKeras works at Keras and TensorFlow. Another important feature is quantization-aware training. I'm going to talk a little bit more about this later. But this is one of the key features missing from the post-training quantization in TF-Lite. We also have the heterogeneous quantization and any number bit width quantization, which is important, and many quantizers. And a few other pretty cool features I'll talk about later. But missing in QKeras right now is native quantization-aware training and the direct TF-Lite support. So native quantization-aware training, I'll talk about this a little later on. This is a very useful feature that's kind of coming more now with the AQT library, which has really introduced it. Oleg talked about this earlier. And the TF-Lite support, this one here is TF-Lite only supports certain kinds of quantization, so you don't always want to use TF-Lite. But yeah, we're actually working to integrate QKeras into TF-Lite in the near future. So how does quantization work, right? It's important to have a conceptual understanding of what's going on here. So on the left, you'll see here like a normal convolution layer, right? It's very simple. Weights, convolution, you add the bias, and you have your final activation. What we're doing here is something called simulated quantization, where we're adding a weight quantizer, a bias quantizer, and an activation quantizer. What that allows us to do is take the floating point weights and then quantize them to some fixed point representation. And I'm saying fixed point here because we can choose where that decimal point is, right? It doesn't have to be an integer. And we can do this for different bit widths for every different quantizer, right? So the weights, the biases, the activations, they can use different fixed point representations. And it's simulated here because the convolution operation is still in floating point, right? You can see here fix, fix, and then float out. So in the real hardware, you probably don't want to do this, right? You don't want to run any floating point convolutions. But while training, this is actually pretty effective and gets you pretty close to what you want to do. And then in hardware, you can make everything fixed point after the fact. So simulated quantization is definitely a useful tool here. And then, like I said before, quantization-aware training, right? Like we have this graph, we have this convolution, but we need to update these weights. Using quantizers adds something of quantization noise, right? It removes information. So if we just remove information, we can't really expect the model to perform the same way. That's why using backpropagation and training these weights, we can help them to take into account that quantization noise that we've introduced. So model accuracy is going to be far better when you do this quantization-aware training that we do in QKeras. So QKeras works by wrapping these operations, right? So conv2d is just the Keras layer. We're going to add some quantizers, and now we're going to call it qconv2d. Okay? Same thing for the activation, just add a quantizer. And we've implemented a bunch of layers here, right? All the way from dense to convolutions, separable, LSTMs, etc. And we're constantly adding new layers because it's easy, right? We can wrap the existing Keras layers. Now let's talk a little bit about these quantizers, right? So we have here the weight bias activation quantizers. How do those work? The math is actually not too bad. All you do is you take some value, you divide by a scale, you round, and then you multiply by a scale. But to do this effectively, you need to know essentially two things. You're binning these values, right? You need to know the size of the bins and the number of bins. You can think of it as the range versus the precision. And the key number here is the scale. So if we just did int x like this, no scale whatsoever, if our values are between 0 and 1, well, that's not very useful, right? We go from some float value to essentially nothing. So we definitely need a scale. So let's add that in. So to find the scale, we're going to look at the max of the inputs and divide by the number of bins. That's going to give us some floating point value. Now we can divide by the scale, round, and multiply by the scale again. And that gives us something that looks like this in red. OK, so much better. There is a problem, though, is that we need to know the max of the inputs. So here. So for weights, this isn't a problem. But for activations, it can be problematic since your inputs are going to keep changing depending on the input to the model. But I'll talk about how to solve that later. And then we have power of true scale. So this is even more optimal because we can restrict the number of steps we have. So if we restrict the scale to 1 over 2 to the number of bits, now we can do a shift operation instead of a multiplication. And shifts are much cheaper in hardware. So overall, we probably want to use the power of true scale as much as possible to make our quantization cheap and effective. So we've implemented this in QKeras using our most popular quantizer function called quantized bits. And it works by, you take some continuous range and you discretize it into these steps. Now you can also, you can select how many steps you have, so the number of bits, and you can also choose the scale here, either auto, like we looked at before, the floating point scale, or the power of true scale. And then we have a bunch of other parameters like the number of bits total, the integer, which is a sort of scale, right, choosing where the decimal point is, if you want to keep negative numbers, etc. We also have other quantization functions, right? Like the quantized bits is not the only way to do this. So quantized PO2 is interesting because it allows us to do non-uniform quantization in preserving both precision and range. So we can have a lot of really granular steps in the center here, but still preserve that range by making these bins get bigger and bigger as you go away from that center. So this can be really useful for certain models and certain applications, and always worth trying out. So that's just a very small glimpse of what QKeras offers, right? We have so many different quantizers, from stochastic to binary. Daniele showed some really cool binary models earlier, to ternary, etc. So yeah, and in addition to all this, in addition to all these quantizers, you can make your own. All you need to do is import a base quantizer class and then create a call method here, right? And in the call method, you can use arbitrary TensorFlow logic. So in these few lines of code here, I've made a little, ternary kind of quantizer, just a couple steps. So very flexible. Okay, that's a lot of information. Let's just give you an example, just to put it in action. Okay, so you're developing your ML model. You have this Keras model, right? Convolution activation and a dense layer at the end here. How does it look in QKeras? Looks like this. Okay, lots of code, but it's not too bad. First step, add a Q. Okay, when in doubt, just add Qs. It makes everything quantized. So here you have, right, you wrap it, use the wrapper to create the QConv2D layer and the dense layer. Second step, add weight and bias quantizers. Okay, so you see here quantized bits. You remember that from a few slides ago. Another thing to note, you notice the bits are all different, right? Some are 4 bits, some are 6 bits, right? This is called heterogeneous quantization. And it's super, super important because it allows us to lower the bit width, right, the cost of layers that don't need high precision quantization, and increase the bit width on layers that do need quantization. It also makes the design space a lot more complex, but it's often worth it because you can find a more optimal solution here. Okay, and then final step, quantize the activations. So here, yeah, we take the Q activation layer and we add quantized ReLU. So that's similar to quantized bits, but now we added the ReLU activation built in a very hardware-friendly manner. So this is what it looks like at the end. Keras model over here, QKeras over here. You'll see that at the end here, we have some interesting statistics. So look, you can see here, you have this many signed 8x8 multiplications. You have this many 4-bit weights, this many 6-bit weights. So QKeras is automatically understanding the model that you've built and giving you these statistics. There's a few other advanced QKeras features that are very important to make state-of-the-art quantized models. One of them is folded batch normalization. There are other libraries that have this, but the basic problem here is that many ML models have this batch normalization layer, right? It's very expensive, though, because you need these high-precision divisions. So how do you fix that? You fold it into the operations of the convolutional layer. So this has very little to no impact on the hardware, but it allows your model to be much better in terms of accuracy. And we have a function in QKeras to just do this for you, right? Convert to folded model. So remember before, near the beginning, I said something like, oh, to find the scale, we need to know the maximum of the input, right? And we know the maximum of the weights, but how about the activations? So this layer here solves that problem of figuring out the maximum range of the activations by using an exponentially moving average. So as we train, we look at the distributions coming into the quantizers and take, like I said, the moving average of that. So that allows us to use an algorithm to basically find the optimal scale for all the activation quantizers as you train. Okay, and this definitely helps model accuracy as well. Okay, one of the final really important tools in QKeras is QTools. QTools helps you in creating hardware implementations of your quantized models. And the way it works is that you give it a quantized model, like a QKeras model, and it creates a data type map of each layer and all of the variable sizes, quantizer types, bits, etc. Everything you need to implement your hardware. So I'll show you an example. Here's a simple model. We say run qtools.qtools. We give it the model, define a few other configurations, and we get this out. So if you look in detail, you see here, we have, for example, our weight quantizers, right? Quantized PO2, you remember that, the bits, all the parameters here. And we'd have that for every layer. We also have, for example, the multiplier types, the number of bits we need there, the accumulator, all the data we need to build the hardware. But what's more is that we can use this for energy estimation. So again, Q energy, right? Let's look at all the different parts of a layer, the input parameters, operations, and outputs. Now we can look up the energy needed for every operation, right, as some reference, and we can add them up. So now we have an estimated energy used by the entire model when you run inference. Perfect. Keep in mind, though, this is an estimate. So the actual energy is going to be some constant times your estimate plus some other constant. But that's okay, right? Because all we care about is the rank order of these estimates and the relative difference between our different models. So if one of the estimates is lower than another estimate, that's still going to be correct in the final implementation. So you can use this to do AutoML. You can use this to do neural architecture search. Okay, so there's a lot of design space options here, right? You remember when we wrote the code, all the different bits, the scales, the quantizer functions, etc. How do we search all of these things, make the perfect model, right? We want an optimal model that has, say, the lowest energy and the highest accuracy. So to do this, we're really trying to find the Pareto frontier. Now, you've seen this graph many times throughout the summit. I just want to put it in words here, right? So Pareto frontier, we are trying to find this curve here such that for any given model cost, we will know the best accuracy at that cost. So for any budget you have, right, you can go along this line here. Okay, what's my budget? Okay, my budget is this. Let's look at the accuracy. This is the best possible model you can get for that cost. Now, I will say here, when I say cost, what does that mean? Right, that seems a bit abstract. Well, it could be anything. It could be the Q energy numbers that we talked about before, but it could also be some cost model, right? So you could take, for example, some of your models, run them on actual hardware, and see what that cost is in terms of, say, latency, area, etc. And then you can make some model that, for any other given architecture, predicts that latency. So then next question, obviously, how do we find that frontier, right? Like we can do some random searches, right? Maybe we can just randomly try a bunch of different options and see where we get. But that's not good enough, right? Sometimes the design space is so huge that, you know, maybe grid search doesn't cut it. And in that case, you can use Google Vizier. This is the second tool I want to talk about. And this is also open source, right? So Google published a paper describing the algorithm. And how it works is actually pretty straightforward. So there's a Vizier API that starts up a bunch of workers. Every worker tries a different hyperparameter configuration, including different configurations for the model architecture, right? So it can try a different number of layers, different connections between layers, different quantization types. And then it has a persistent service here that suggests new trials. Right? So once it has a feeling of how the model is doing with certain layers or quantizers, it can use that search to find better models that will perform better next time, right? And it'll just dynamically create workers to search these configurations in parallel. I'm often starting up, tens or hundreds of workers to run in parallel to find the best options that I need. And in doing this, it's optimizing multiple objectives. It has built-in support for this. It's trying to minimize some cost and maximize, say, the accuracy. What it allows us to do is really push this Pareto frontier as much as possible to the top left, right? That's really our goal. It has a few different search algorithms to do this, including grid search and random search. But the real nice one is Bayesian optimization. So this animation is not running. But essentially, the gist of Bayesian optimization is that you start with a few random points, and then you build some sort of probabilistic model of where is the next highest probable parameter to try to maximize that model accuracy or minimize the cost. And Bayesian optimization here is a simple algorithm, but it's really effective for doing these kinds of searches where it takes a long time to try every new model. There's two ways to use Vizier. With Google Cloud, that's the easiest one. And here it's called Vertex AI Vizier. Okay, you can Google that. There's a free tier available, and I think for universities, there's also some related credits, so definitely give that a try. There's also an upcoming open source version on GitHub. And this one will also support custom search algorithms, so you can get really fancy in how you want to optimize that Pareto frontier. I'll briefly show you some code for how to create a Vizier study. Here we can define some parameters. So here I just defined this parameter of, let's say I want to search the weight quantizer bits from 4 to 12. And then I have a bunch of other parameters like this, let's say. Then I have some metrics, like I want to maximize accuracy, minimize cost. I plug it into the study dictionary, and then I send it to the Vizier client. Okay, that's it. I've made my study. Now the workers execute this code. They ask Vizier for a suggested set of parameters to try. They get it in some config and create a model, right? Say create some QKeras model based off of that config. Then they train the model, evaluate the model, and then report back to Vizier. This is what I found. This is how the model went. And after a bunch of workers do this, you can get a result. So this is called a parallel coordinates visualization. Really nice thing to use. You can essentially highlight a section of parameters. For example, I'm going to highlight all the models that have the best accuracy here. And the red lines show me every other trial, or every trial that hits that best accuracy. So I can see a good correlation between high accuracy and, say, whatever this parameter is, the activation, right? Or maybe there's low correlation with some other parameter. Okay. I'll just quickly mention there are such things as learnable quantizers, where we can actually use backpropagation to learn that scale and the number of bits and the range. This is more state-of-the-art research, and this can also help us reduce the search space size. So definitely something to keep an eye out for in the future. And then I'll go a few seconds over time. I'll just mention a quick case study where our team actually published to Nature in a collaboration with where we showcase some of these techniques for quantized models. So the task here was there's a collision and a spray of particles. And we need to classify the different particle types into a few different classes. Now, because this is CERN, right, they need to run these models extremely quickly, and they need to be extremely small, right? So to do this, we can't just use a normal TensorFlow model. That's way too big. So what the team did, they used something called AutoQKeras, which Vizier you can consider of as a next iteration of AutoQKeras. It has a few more features, but the concept is exactly the same. Right, so they did some neural architecture search with QKeras tools and QKeras tools. They then ran HLS4ML and got basically an RTL out that you can run on an FPGA. So the results were quite good. You can see the last line here, they got about 75% accuracy or so. And after doing the search with QKeras, they were able to go from this already pretty good quantized model to one that has 25% the energy and still has about the same accuracy, so only about 1 or 2% drop in accuracy. So really effective technique here. And this is what it looks like at the end, an ultra-compressed deep neural network for particle identification on an FPGA. That's it. Thank you.
Thank you, Daniele. We have time for questions. 3 minutes, please. So a few questions.
Hi, I have a quick question. Thank you so much for the great talk. So the simulated quantization, I'm curious, like, how does it work with backprops? Are those kind of operators differentiable?
Yeah, that's a good question. So they're not differentiable, but we can use something called a straight-through estimator. So the basic idea here is that instead of going through the weight quantizer, we have an identity operation here that we just, instead of going through the quantizer, we go through the identity operation and then go through the weights. So it's not perfect, but it works pretty well.
I see. Thank you.
Yeah, I had a question about the Vizier service, mostly on the Bayesian optimization side.
Yeah.
What process are you using to approximate the surrogate function, and what are you using as the acquisition function?
Okay, so the optimization is, the metrics that you must optimize are reported by the workers, right? And those can be any scalar values that the workers report. Now, as to the details of how the Bayesian optimization works in and of itself, I'm using Vizier as a black box optimization, right? In the open source version, you can go in and tweak those parameters. As to the exact details of that, I would say read the paper, and we can also talk afterwards. But yeah, they're doing some pretty cool stuff.
Okay, yeah, and also another question is, like, how are you doing the clustering from the workers at the end? Like,
how are you what? Sorry.
Like, you have like several workers,
yeah.
And then they're obviously gonna use the error to propagate forward, like do exploration and exploitation, which that's why you see this curve in the, I guess, the parallel coordinate plots. I was wondering, like, what algorithm are you using for that, clustering the decision from all the workers? Because I read the paper, it was actually not clear, like, how these things are working.
Yeah, we'll have to talk
I
about
think we
that
can
for
talk
that.
through it,
I
that's
think
fine,
there's more
yeah.
details in the paper. I'm using Vizier mostly as the black box
No, it's fine.
optimization
Yeah,
service.
no worries. Yeah, sure.
Yeah.
Thank you.
Yeah.
Hi, great talk, awesome tool. I'm from Bloomerai, so I've actually worked on Lark a little bit. And I was wondering if you could go back to the slide for the comparison.
Yeah.
You mentioned the direct TF-Lite support. What does that mean in this case?
Yeah, so I will say take this comparison with a grain of salt, right? So direct TF-Lite support. QKeras, we can create any bit quantizer, right? But TF-Lite, right now, you can only do 8-bit and floating point, I believe. So that means that we could only use QKeras quantized bits with that 8-bit quantization. So for that reason, we don't export directly to TF-Lite. But here's the thing, TF-Mot does. And TF-Mot is a pretty cool tool where we're working with them right now. And in the near future, you're probably going to see more of these QKeras features put into TF-Mot. So keep an eye out for that, where we can go directly to TF-Lite. But just remember, TF-Lite, right, like the really cool stuff here is this heterogeneous quantization. It's this low-bit quantization. And personally, I'm really looking forward to TF-Lite adding some more of these features where we can do this quantization.
So do you expect TF-Lite Micro to add more extreme quantization functionality in the near future?
I really hope so. That's all I can say.
Cool,
Yeah.
thanks.
I'm sorry, we are exceeding the time. Unfortunately, I am the timekeeper. I'm sorry. Please feel free to meet Daniele also after the meeting. Now it's the thank you so much, Daniele.
Thank you.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Syntiant. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinymL forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors, Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Gravity, Hymex, HOTG, Imagimob, Itemis, Lattice, Nota, OmniML, Pixart, Bloomerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support and, more importantly, for them being part of this community and driving it forward.